Thank you for the introduction, and thanks everyone here during your lunch time to come to my session. My name is Yanbo, and currently an Apache Spark committer and software engineer at Hortonworks. Today I will talk about our old topics, CTR prediction, but the CTR prediction on Spark may be not that old. CTR prediction plays a very critical role in search or display advertisement, which is almost the most successful internet business model during the past decades. But not all companies is like Google or Yahoo or Facebook have to build their infrastructure from scratch. And a lot of other companies from all kinds of size has requirements to use CTR prediction. This is very similarity problems they called like CTR. So Spark is widely used in all kinds of companies of all sizes. So we can leverage Spark as the infrastructure to build a CTR prediction pipeline, even your data set is very, very large. So today I will show our experience about the work on large-scale CTR prediction with Apache Spark and some deep learning engagement. And we will focus on how to use Spark and deep learning to solve the problem rather than innovation in CTR estimation theory. Okay, our talk is organized as an evolution of our CTR estimation pipeline using Spark, from the basic solution and then to a more scalable solution. The more scalable solution is leverage a scalable linear model and optimizer implement on Spark, which will train a very scalable model, can scale to billions of features. And finally, we provide an advanced solution, which is an attempt to learn part of features from deep neural network. Okay, let's first start with the basic pipeline. This is a typically CTR estimation workflow, which mainly involves 3 steps: the feature engineering, the model training, and online service. It's not surprising that the most important thing is to have the right model and the right feature. The right feature is that capturing the historical information that about the users or advertisements that dominate other types of features. Once we have the right features and the right models, other factors will play small roles for your improvement. So let's focus on the first 2 parts of the workflow. And how to do feature engineering depends on the model you're using. So we need to pick up a suitable model before start work. As we all know, advertisement CTR prediction model with billions of features is very common in industry areas since it's real big data problems. And at such large scale, nonlinear models can scale well and involves a lot of technical complexity. So it's also very important to train a model, can be interpreted and can be debugged more easily, since any small change is possible to lead to huge loss on revenue. So we need to carefully to choose a model and need the model to be interpreted. For the above reason, linear model, especially the logistic regression model, is widely used. Especially the logistic regression is widely used in industry system for CTR estimation. In practice, we usually train logistic regression model with the L1 regularization, which can produce sparse coefficients. The sparse solution is also more efficient when and require less memories when making prediction when serving your model. So linear model is widely used, but it can only learn linear relationship between the features and the label. So to get a more accurate model, it requires manually build up some high order or nonlinear relationship or nonlinear combinations features from scratch. Let's find out Spark can help us on the feature engineer. Usually, typically, the most popular feature transformer is such thing like one-hot encoder for categorical features. I think most of you may be familiar with the one-hot encoder. And for some nonlinear features, there are 2 simple ways to transform the input features into nonlinear space. For the continuous features, to bin the features and treat the bin indexed as category features. And then the linear models can effectively learn a piecewise constant nonlinear maps for the feature. So Spark provides context descriptor and string index to handle this case. And for another kinds of category features, we need to calculate the Cartesian products of the original features, as known as the feature cross or feature combination. For example, you can cross the three features like age cross gender cross states. For example, you can mean a 30-year-old male man from San Francisco has more possibility to click this advertisement. So this feature cross will make a linear relationship between the combined features to the label. So usually this is very, very useful feature transformations for get the nonlinear features. But usually the Cartesian product is very, very large, and not all of them are very useful. So we need lots of experience to get the useful combinations. So, but we can say that the computing the cross between all features is equivalent to consider a polynomial kernel of degree 2. Spark provides a polynomial expansion transformer to handle this case, and you can use your own customized transformer to finish this, since you may not need to cross between all features. So it's not very hard to build a basic CTR estimation pipeline on Spark. First, we join different data sources, including the query, the impression log, and the click logs, and all kinds of advertisement and user-related metadata, and make feature transformation and selection, assembling the selected feature together, and then we fit them with the Spark MLlib logistic regression model. At last, we calculate the binary classification matrix to evaluate the performance of your model or your pipeline and choose the best one to use. However, after the feature engineering, the number of features will be expanded, and it's very easy to reach 1 million or 1 billion or more. So according to our experience, currently Spark MLlib logistic regression can only scale to tens of millions of parameters. It can't satisfy the typically CTR estimation use case with billions of parameters. So the most challenging problems is, can we figure out a way to train a very, very scalable logistic regression model or other kinds of linear models in Spark environment? The following part is a major contribution of our work. We have implemented vector-free L-BFGS as a general and fully distributed optimizer on Spark, and some linear models based on the optimizer. So let's first have a look at the bottleneck of current MLlib logistic regression, why it can scale to billions of parameters. This is the workflow of current MLlib logistic regression. In each iteration, we start with broadcast coefficients to exactors, and then compute the loss and gradient in parallel in all exactors, reduce them to get the loss sum and gradient sum in driver. And then we use Breeze L-BFGS to solve the optimization problems as drivers, known as find the next direction by estimating the inverse Hansen matrix. The bottleneck is after we collect gradient sum from exactors, we need to store and compute it in driver to find the next directions. If they scale the numbers of features to billions, the variable used by L-BFGS can't be held in a single memory. And it will also need a lot of CPU workflow, CPU resource to calculate the two-loop recursion during the L-BFGS and make it very hard to be finished in reasonable time. And for advertisement, CTR estimation is very common. The feature dimension is more than 1 billion. Take an example, if we set the L-BFGS history size with 10, it will produce 21 billion variables, which required 84 gigabyte memory to store the history, states, and gradient during the L-BFGS for a Spark cluster built from commodity hardware. This is generally unfeasible. So a very intuitive idea is to make it distributed. We not calculate and store them in a single machine. I heard a lot of Spark users complain that the MLlib model is not model parallel, it's only data parallel, which restricts the usage of MLlib in their use case. So we developed an open source vector-free L-BFGS. We call it VL-BFGS on Spark, which eliminates these restrictions to make both data and model are parallel. We implemented the VL-BFGS on Spark under the inspiration of this this paper. This paper was was first released by Microsoft. If you want to learn more details about the implementation on Spark, please see my talk at Spark Summit East at Boston. And in summary, we store model coefficients and all necessary variables as a distributed vector. It's not a vector in a single machine, it's a distributed vector. And the distributed vector will be stored across all Spark extractors. So we use RDD to store the values of the distributed vector. And each line of the RDD is a MLlib vector. So the model is parallel essentially and can be scaled to billions of parameters. And also we implemented logistic regression on vector-free L-BFGS. The L-BFGS-based logistic regression can produce a parallel model essentially on the parallel data. So in the existing MLlib framework, we only split the RDD in horizontal direction, but in the L-BFGS-based logistic regression implementation, we split the input RDD both in horizontal and in vertical directions, since both the instance number and the number of features are very, very large. So we have very expressive slides to depict the procedure of logistic regression implementation on L-BFGS. If you are interested, you can also refer my talk at Spark Summit East. Now we have open sourced the Spark L-BFGS and corresponding linear model implementation on GitHub under the Apache license. Currently, we have got more than 1 production users and more than 3 experiment users to try to train model with billions of parameters. There are 3 contributors from different companies has made contribution to the open source project. Thanks for all the contributors. So if you have similar requirements, please feel free to give a try. And in the following, let's take a look at the API. The API is very, very similar with the MLlib API. Is only adds some extra parameters. So if you are familiar with MLlib, you can easily to use it. And this is the total key takeaways or key features of L-BFGS. And you can just say it's a fully distributed calculation, fully distributed model, and since it's fully distributed, so it can run successfully without OOM. And the API is consistent with L-BFGS. Output is exactly the same. So you can use it safely. You don't care. You don't need to worry about it can produce the result exceptionally. And it can also implement some other linear loss functions on this optimizer, since a lot of companies will export their own loss functions. And it don't need any special components such as parameter servers to handle a so large scale case. And if you have already have a lot of Spark cluster operation and management experience, you can get benefit. And since it's a pure library on Spark, you can use the same platform as the data size increasing. If the data size is small, you can use Spark MLlib. If your data size is increasing and feature increasing, you can use our Spark L-BFGS. So this is the performance. In general, we can say that L-BFGS didn't behave better than the MLlib when your number of features is less, such as the number of features is in less than tens of millions. The existing MLlib logistic regression may be behavior better. But when we increase the number of features to more than 50 million, the existing MLlib logistic regression will fail with an OOM out of memory exception. But L-BFGS can still success. So we update our CTR estimation pipeline to a more scalable version using our logistic regression based on vector-free L-BFGS to replace the old Spark MLlib logistic regression. So the offline experiment comes from one of the users of Spark L-BFGS package, which is an industry website, has more than 100 million users. The total training data has about 2 billion instances and another 500 million for testing. There are about 600 million features per instance is not 1 billion, since in this case it's only reached 1 billion, but not exactly. And the number of non-zero features per instance is about 80 on average. So, and in our users, they were using Spark MLlib logistic regression to train the CTR estimation model originally. However, due to the scalability issue, they can only add parts of the feature class. Since we say that feature class may be very, very large, they only add a part of feature class to capture the nonlinear relationship. We use the old model as the baseline, and all other experiments are compared with it. The model is evaluated based on the text limit using AUC. It's very popular metrics. Since we are not allowed to exhibit the exact AUC number due to the privacy consideration, we report the relative change compared with the baseline. And the help of L-BFGS, we can add more features crossed. Also, the combination of the features were determined empirically. We got AUC gain at about 1%. It seems small, but it can also make a huge difference in advertisement revenue. Our users has pushed this model into productions, and it also gets gains for online service. But we can't also share. We also can't share the details due to their company's policy for the online result. But we can tell you it gets gained. Okay. Until now, we got a better model than before. And we can have a rest. We recap and summarize the lessons we learned when we get together to grab a cup of coffee. The improvement is mainly due to it can train a more scalable logistic regression model, which means you can add more useful features into the logistic regression model. And another part comes from you can get more effective nonlinear features. But the effective nonlinear models is caused by more experienced engineers, so we will not show the details. And for the more scalable logistic regression model, from the engineering perspective, we have encountered a lot of challenges when we do it. The most challenging thing is to handle unbalanced data. L-BFGS and corresponding logistic regression implementation involves lots of Spark jobs with many stages, since all of the calculation is calculated by Spark jobs. So the unbalanced data will lead to stragglers, which slow down the whole training process. We use hash tricky when generate the block metrics like we depicted before in previous slides. So we use the hash tricky to generate block metrics used at the beginning of training. But this is also very, very challenging. We still need to find a better way to handle this matrix conversion from the RDD to the data format that can be fed to logistic regression on L-BFGS. And another one is from the original RDD of instance, we need to repartition it to block metrics for training. We have did some value combinations and compressions to reduce the shuffle amount of data, and it has been reduced from several hours to several minutes. The core operations of vector-free L-BFGS is calculate dot product between 21 distributed vectors. Since we calculate the dot products between distributed vectors is very time-consuming. So we design an efficient way which can reduce the number of jobs for the steps from 42 to 1 and makes jobs can running more parallel. You can save a lot of time. And another significant optimization is we store sparse metrics in COO format, which is currently not supported by MLlib. And it can reduce the memory use by about 30% and make the computation more efficiently. So this also from the engineering perspective we have done to make the L-BFGS running more fast. Okay, After that, we will think, is this a model is good enough? And do we have some room to improve the model? We can say this slides show the linear model or logistic regression model used as the last step of the pipeline. All features, combinations, and bookies are hand-designed, which can leverage the understanding of the domain knowledge. This will lead to a stable or optimal results, but it involves heavy physical work and need to hire a lot of experienced engineer. Can we learn feature combination or high-order features automatically, like what deep learning can do? So we have exploration on more advanced model to use deep learning, but as we all know, deep learning can used very, very successfully at image processing, at computer vision, at speech recognition, and natural language processing. But the data used in CTR estimation is very sparse with very high dimension. And that is different from the data used in computer vision or natural language processing. So can we train DNA models used by CTR estimation is also very, very hot topics during the research and industry areas. Training a deep neural network on a large and sparse input feature space requires tuning a huge number of parameters, which is hard to train traditional deep neural networks in reasonable time. It will take a lot of time to train, and it also take a lot of time to make predict. And so even we get a DNA model, the response time of model serving is still can't satisfy the online prediction requirement. So even the full connected DNA model can get more accurate on the than other models. It's still very hard to directly push it into the model serving. So this is why linear models are still the most widely used model for CTR estimation. But we want to know, can we figure out a way to combine the advantages of both linear models and DNA models? As we all know, in a deep neural network architecture, the output of each intermediate layer can be viewed as a representative of the original input data. So in our updated solution, we use DNA to learn some high-order features and then fit the features into a linear model at last. This is the architecture of our solution, our updated solution. We keep the raw category features and the most relevant class features as part of the linear model input for some of the raw category features. And some of the continual features, we put them into a DNA to learn other high-order features. For the category input of the DNA, we will embedding them into low-dimension space and then fit in a DNA classification models. We select the last hidden layer as a new high-level representation of the features and then fit them into a linear model. Note that we only choose the features that will not update very frequently as the input of DNA, since the DNA training is very slow, such as statistic features and some user demographic features. We don't need to retrain the DNA model very frequently. So the raw category features and selected category features are also used. And they are very, very sparse and in a very large space. And we add more DNA features. The DNA features is very dense, but the dimensions is usually not very high. So here we still get a very large feature space, and maybe a little denser than the previous model, but we still get a very high dimension feature. We still need to use the Spark L-BFGS to train the linear regression model. If we dig deeper into the DNA model, is a neural network with several layers. We learned 20-dimensional embedding vectors for each category features, and then concatenate all the embeddings together with the raw continuous dense features, resulting in a very, very dense vectors of about 1,000 dimensions. So then we connect the vectors, all the connected vectors is then fit into 3 IRU layers, and then finally the logic output units in the deep neural networks, we extract the last hidden layer in the IELU layer of the DNA as the input of the previous linear model, as part of the input of the previous linear model. So now we have updated our CTR estimation pipeline. We learned features from DNA via TensorFlow. The DNA feature learning operator is equivalent to other feature transformers in Spark MLlib pipeline. Since we don't update the DNA model, DNA feature very, very frequently, we don't need to retrain the DNA model each time when we retrain the whole pipeline. So we can use it in model transformation directly. And then how to integrate the DNA models training into the whole pipeline, leverage the big data infrastructure and hardware support like GPU. There are a lot of different companies propose different type of scenarios for their use case. And I have another talk at next week at the Databricks Summit, San Jose, to explain how to integrate Yang, Spark, and TensorFlow to boost their machine learning applications. If you are interested, you can visit there, or you can watch the speak at YouTube. Okay, and after we get that features learned from DNA, we got another AOC gain for offline experiment, but not very significantly compared with the last experiment. This is just the first attempt to train DNA feature in our experiment, so we don't have enough time to do enough tuning for this neural network. I think there will be small room for improvement, and currently our users didn't push this model into online, since they have a little worry that the DNA model whether can get revenue gain in online service. So we still make a lot of exploration and improvement for this updated model. So even the experiment is offline and we didn't push it into online service, we can also learn that the DNA model is a promising way to learn high-order features from raw feature input, since it can get another kinds of representations of the raw features. And it also can reduce some dependency to heavy physical work of hard design feature combinations. However, training deep neural networks on a large data set with a large feature in space usually need to tuning a large number of parameters and need a lot of computer resource, which is very expensive and need a lot of time. So we only need to feed features that not change very frequently to the DNA models. So our DNA models is not very, very big. We have only several years, and the dimension of the embedding is also not very large. So at last, we still use the linear model as the last step to satisfy the requirement for training and prediction. This is a requirement from the online CTR prediction. So this is the lessons we learned from the advanced model, CTR estimation model. Okay, and thanks for all the contribution, all the contributors to the Spark L-BFGS project, and also thanks Xiangrui from Databricks to give some guidelines during the implementation of Spark L-BFGS. Thanks.
We've got a few minutes, so if you have a question, go ahead and raise your hand up, and I'm just going to go and run on over. So, do you have a question?
Nice talk. My first question is, how do you handle unbalanced data? Is downsampling, or I think I didn't get the, how do you handle unbalanced data? Because usually negative example is much
okay. Oh, I think I didn't explain the scenario very clearly. The unbalanced data, what I described in my slides, is not the unbalanced label. Unbalanced label is usually we use some subsample to, you can check this pipeline. Okay. Currently, actually the stratified sampler is what you want to do for subsample the data, the unbalanced label. What I means unbalanced is during the computing of the VFGS, we need to repartition them, and each line we have different non-zero values. So if it's not very balanced, we need some jobs run very slow and others run fast. And the synchronized model will make with the struggler to finish, so we'll make the whole process very slow.
Okay.
So this is different.
Okay, I see a different meaning. Okay. The same question is like when we do the categorical data, you try mapping the feature string to the index ID. Usually, with a lot of, feature a lot of feature, then probably I think Spark probably has some constraint for those ID mapping. So I'm not sure how many features you're training.
Okay.
Do you do the feature trick or hash?
Okay. I see. What you want to know is we have a lot of ID features like ID of user or ID of advertisement, and how did to transform it to the feature space and then we can fit it into the pipeline. Okay. Currently, this is a very good question. Currently, we have one hot encoder. It can handle parts of the work, but I think the feature space is not good. Yeah, we have implement a separate transformer like it. Currently in the pipeline, I didn't explain clear. The string indexer and the feature interactor both are our customized transformer. And for the string indexer, we need to support multi-columns. We need to support index multi-column strings at the same path of data. And for your case, it's also a very important case. We make it make the RDD split not in horizontal direction and in the vertical direction. So it may be slow than the previous one, but we can do it. You can check the code at the Spark L-BFGS GitHub. We have do it split in both directions to have it happen.
A lot of features. Do you do the feature hashing or do you do any feature trick, like say maybe?
We currently didn't do feature hashing. Currently in current pipeline.
We're competing with lunch now, so I think Yanbo is going to stick around for a little bit, and he'll be able to, because I've seen a few hands and we just didn't have enough time to get to him. So go ahead and head up front. Yanbo will be here for a little bit, but otherwise, thank you very much for an excellent talk, and thank you for contributing to Apache Spark.